Welcome to this explainer. We spend our entire days tapping on smartphones and interacting with servers, but rarely do we stop to think about the literal atomic mechanics making them function. So today, let's unpack the physics and mechanics of semiconductor junctions.
But before we can even begin to understand how these microchips process billions of calculations a second, we have to ask a deceptively simple question. What actually happens at the atomic level the exact millisecond two different electronic materials physically touch? It sounds basic, right? But trust me, the reality is a highly chaotic, dynamic environment.
To figure that out, we're going to build our understanding step by step. We'll meet the p-n junction, dive into the physics of contact, explore the depletion region, look at bending energy bands, tackle the Fermi pinning anomaly, and finally, see how this powers the transistor.
All right, let's jump straight into section 1, meet the p-n junction.
Okay, so we absolutely cannot talk about semiconductor junctions without first understanding the baseline metrics that govern them. The absolute most crucial concept here, the Fermi level. Think of this as the ultimate baseline energy metric for electrons inside any material. In formal terms, it's the thermodynamic work required to add one single electron to a solid-state body. It essentially represents the electrochemical potential of the material, and it is the key to figuring out its electrical properties.
To put it in statistical terms, imagine the Fermi level as a hypothetical energy tier. At thermodynamic equilibrium, this specific level has exactly a 50% probability of being occupied by an electron at any given time. Basically, it dictates the statistical odds of where electrons are actually going to sit inside a physical structure.
Now check this out. Look closely at the band gap. That's the space between those energy levels. What's wild is that within the semiconductor's band gap itself, there are absolutely no available states for electrons to occupy, literally none. Even if the math says there's a non-zero probability, if it falls right in that gap, nobody is home. At absolute zero, every single state up to the Fermi level is packed completely full, and everything above it is entirely empty.
Moving on to section 2, the physics of contact.
So now that we know our main player, the Fermi level, let's look at the state of affairs right before contact. Imagine we have a p-type material, which is packed with holes or positive charge carriers, and an n-type material, heavily loaded with electrons. Before they touch, they're just minding their own business, completely independent. They've got their own work functions, and crucially, their own separate Fermi levels. They are just sitting there in their own isolated states of equilibrium.
But the very millisecond that they physically touch, boom, everything changes. Electrons from the N side naturally want to surge across that metallurgical junction right into the P side, while the holes diffuse in the exact opposite direction. And this sudden massive migration leaves behind bare ionized dopants, positively charged donors on the N side and negatively charged acceptors on the P side. Suddenly, they're exposed in a violently changed electrically active environment.
A great way to visualize this is to think of two big glass beakers filled with water to completely different heights. Those heights represent our initial, independent Fermi levels. Opening a tap between those beakers is exactly like bringing the two semiconductors into physical contact. The water is going to rush and flow until the levels are perfectly even, right? It's the exact same physics here. The Fermi levels must shift and equalize until a unified thermodynamic equilibrium is reached across the entire newly formed system.
Which brings us to section 3, inside the depletion region.
So that sudden chaotic rush of particles trying to equalize the system actually creates a highly specific, localized area right at the border. We call this the depletion region. And inside this region, we are basically watching an epic microscopic tug-of-war. On one side, you have diffusion. That's the majority carriers wanting to naturally spread out from high concentration to low. But on the other side, you have drift. Remember those bare ionized dopants we just talked about? Well, they create a very powerful, built-in electric field that furiously pushes those diffusing carriers right back to where they came from.
Now, this isn't some endless battle. The depletion region expands precisely until these two opposing forces completely and perfectly cancel each other out. For each individual carrier, the diffusion current exactly matches the drift current. Once diffusion equals drift, a dynamic equilibrium locks in, and the expansion of the depletion region just stops.
Let's see what this actually looks like in section 4. Bending the energy bands.
Because that newly formed depletion region holds a net charge from all those exposed ions, Gauss's law tells us something really fascinating has to happen physically. The actual electron energy bands must curve.
As you move from the p-type across to the n-type material, you get this very distinct downward curvature in the energy bands. And it's super important to note here that net charge strictly means curvature of the bands. The neutral regions outside of it, absolutely no curvature at all.
And this total curvature isn't just some random shape. It represents the exact amount of internal potential energy, what we call the built-in potential, required to completely stop that initial chaotic rush of carriers we saw earlier. It perfectly equals the original electrochemical potential difference that kicked off the diffusion in the very first place. The complex math and the physical reality align perfectly here, which, let's be honest, is highly reassuring when you are trying to engineer microscopic components.
But things don't always go as planned. Welcome to Section 5, the Fermi pinning anomaly. Because as literally any engineer will tell you, nature doesn't always want to obey our neat mathematical alignments. When you try connecting certain metals to a semiconductor, you would logically expect the energy bands to shift cleanly, to align with the metal's specific work function. But sometimes, the physical interface completely overpowers the bulk properties of the material. The bands of the semiconductor surface violently bend and just lock into a fixed position. We call this anomaly Fermi-level pinning. You can relentlessly change out the metal you're using, artificially increasing its work function all you want, but that energy barrier absolutely refuses to move. It is stuck. This proves that the exact atomic contact point isn't just some passive boundary. No, it's a highly active, totally chaotic electrostatic environment that can completely ignore the properties of the metal you're trying to connect it to.
So how do we actually use this? Let's jump to Section 6, powering the transistor. So how do we actually harness all this wild physics, the diffusion, the drift, the crazy band bending, to build our modern world? Well, we combine multiple junctions back to back. Doing this creates a transistor. Specifically here, we're looking at a PNP layout, which consists of an emitter, a base, and a collector. This tiny, elegant architecture is literally the fundamental amplifying building block of all modern electronics.
By carefully manipulating the voltage across these regions, we can dictate exactly how those charge carriers behave. Step 1. The emitter acts as a forward bias junction, actively injecting minority carriers into the system. Step 2. The intermediate base layer allows these carriers to travel across. And finally, Step 3, the collector, acting as a reverse bias junction, basically acts like a giant vacuum, sweeping those carriers away and out of the system. This perfectly controlled flow is exactly what allows for the amplification and switching that makes all digital logic possible.
Which leaves us with a final, pretty provocative thought. We have spent decades mastering the chaotic physics of contact, brilliantly manipulating Fermi levels and depletion regions to build the digital age as we know it. But as our transistors continue to shrink, getting closer and closer to the literal atomic limit, we have to wonder, are we reaching a threshold where this delicate electrostatic balance becomes completely impossible to tame? Will Fermi-level pinning and violent band bending eventually put an absolute, hard physical limit on how small our technology can actually go? It's a massive question, and it's exactly what the brightest minds in semiconductor physics are racing to answer today.